Hello everyone, we are Team 4 and our 2015 Senior Capstone Project is the Thermophilic Anaerobic Digester. Our group members are Kevin Nguyen, Ben Rukavina, Flora Sue, Wesley Miller, and Ali White. In partnership with the Chittenden Solid Waste District, or CSWD, we developed a preliminary design for a two-phase anaerobic digester facility to improve upon Vermont's infrastructure. The current biosolid disposal system is neither socially, economically, or environmentally sustainable. CSWD transports about 14,000 wet tons of sludge per year from Chittenden County to landfills in Coventry, Vermont, and to the Grasslands facility in Chateaugay, New York. The annual cost associated with the disposal of sludge is about $900,000. Our two-phase anaerobic digester will help Chittenden County be more socially, economically, and environmentally sustainable by producing useful byproducts such as methane and fertilizer. In order for our digester to produce these resources, the wastewater biosolids that feed into the digester must go through multiple complex stages to remove unwanted compounds and various types of pathogens. First, the digester receives solid and liquid waste from wastewater treatment plants throughout Chittenden County. The liquid waste flows in at about 65,000 gallons per day and contains about 2.2% solids by volume. The solid waste feeds into the digester system at about 6,650 gallons per week and has a solids content of 20%. The influent liquid and solid waste flows are combined in the equalization tank to achieve a constant outflow of about 66,000 gallons per day, which has a solids content of 2.4%. The combined sludge then goes through an enhanced biological phosphorus removal system to remove phosphorus from the sludge. The sludge is then processed through a gravity belt thickener to thicken the sludge from 2.4% to 6.5% solids. The excess water extracted from the sludge is pumped to a wastewater treatment plant for further treatment. The remaining sludge is then treated in two 12-hour batches each day. The sludge first passes through the thermophilic digester, which is maintained at 58 degrees Celsius to eliminate pathogens. Prior to entering the thermophilic digester, the sludge from the thickener flows through a glycol heat exchanger, where the previous batch of sludge in the thermophilic tank preheats the new batch of sludge. The new batch then enters a pre-treatment tank, where it is further heated to reach 58 degrees Celsius in temperature before entering the thermophilic digester. After 10 hours, the sludge is pumped out of the thermophilic digester and passes through the glycol heat exchanger again, this time to preheat the next batch of sludge. This helps to cool the sludge prior to entering the mesophilic digester, which operates at 35 degrees Celsius. By recovering the heat from hot sludge leaving the thermophilic tank to preheat the next batch, the amount of energy required to heat the system is reduced. The sludge remains in the mesophilic digester for 20 days to remove at least 60% of the volatile solids. Approximately 65,500 gallons per day of methane is produced in the process. The generated methane is scrubbed of impurities such as hydrogen sulfide and carbon dioxide. The clean methane can then be combusted in a water boiler to supply steam for the McNeil Electric generating facility. Following treatment in the mesophilic digester, sludge is discharged into the belt filter press for dewatering. Finally, the treated biosolids are deposited in a storage tank. If treated properly, the biosolids will have met EPA Class A standards, which will allow them to be sold and used as a land application fertilizer. Along with our two-phase digester design, we have considered three different alternatives, which include a single-stage mesophilic digester, a single-stage thermophilic digester, and a do-nothing alternative. The mesophilic digester alternative would take the place of both the thermophilic and mesophilic digesters in our main design. The mesophilic digester with a volume of 253,000 gallons would operate at 35 degrees Celsius and have a solids retention time of 20 days. The digester would produce Class B biosolids, which is typically deposited in a landfill or used for land application with strict EPA standards. The thermophilic digester alternative would also take place of both the thermophilic and mesophilic digesters in our main design. The thermophilic digester alternative would also replace both the thermophilic and mesophilic digesters in our main design. The thermophilic digester would have a volume of 13,000 gallons and operate at 58 degrees Celsius with a solids retention time of 15 days. The thermophilic digester can handle higher organic loadings than the mesophilic digester and can destroy pathogens in the sludge. The digester would produce Class A biosolids which can be sold for agricultural purposes. The last alternative is to do nothing. In this scenario, CSWD would continue to transport sludge from the wastewater treatment plants in Chittenden County to Coventry, Vermont, and Grasslands facility in New York. A 20-year present worth cost analysis was conducted to evaluate the economic viability of each option. The analysis accounted for construction, maintenance and operation, and an upgrade at the end of 20 years. The do-nothing alternative was assessed to be the cheapest option, and the temperature-phase digestion system cost only $400,000 more. However, this analysis did not account for any financial gain from selling the Class A biosolids as fertilizer, nor did it consider rising fuel costs, which would significantly increase the cost of long-distance waste transport. Our recommended option is temperature-phased anaerobic digestion because it is socially, economically, and environmentally sustainable. Local agricultural business would benefit from Class A biosolids. Taxpayers will get the most out of their hard-earned money, and our carbon footprint would be reduced.